That's why the ideal temperature is closer to the hottest than it is to the coldest, if that makes sense. That's why it's not as bad of a swing.
Sure. Yeah, we're gonna have to agree to disagree. I'll take the cold any day. You know, like you're in a cabin and it's snowing out and you got like a fireplace going, like that to me, I'll take that over the beach.
Yeah, I mean, the students think the assignments are worse than both the cold and the heat. So
yeah. Okay, I shared the wrong thing. I gotta fix this. I have to share the whole screen, not just that thing. All right, let's get started here. I think this week is not too bad, but you know, let me know if there are any questions. I'm hoping that it doesn't kill us too much. What will happen if I should just keep this here. I'll keep that there. No, we're going to have to do math. I'm glad the class is so, like, you know, polarized about this issue.
Yeah.
That needs to be the next poll question, right? Like, would you rather be hot? Would you rather be cold? Inside and outside are F. No, Curdy, I think if you can just explain it, it's fine. If you want to try and set up a different variable and kind of say like, let's treat the inside as this thing, I think that's okay. And might help in terms of an explanation, but it's not necessary.
Speaking of which, we have I don't know if you saw the tutorial question that we're going to be covering today, but it's a really good question. Question 3, that's the one from the textbook, the one with the graph and the limits of f of x and stuff. And I think it's a good question.
Yeah, exactly. Yeah. And everyone, I'm going to call it in 30 seconds here. The class is doing pretty well. I think almost everyone has got it. A couple people, I think, probably just made a little calculation error, but you can see this is the sort of thing that we can do so that you can't, or make it more difficult for you to use a calculator, right? Something like this is, not hard for you to do as a person, but is a little bit trickier to get a computer to do for you, right? So, okay, sweet. Okay, so like 77%, that's a phenomenal number of the class got C, and C is absolutely the correct answer. Let's very quickly talk about it because there's a couple of caveats like, I want to mention a little bit. No, let's not share it. Okay, so this is question 2 of this week's polls, and I think you all correctly identified that basically you can just plug everything in, right? So this is question 2. We were told that the limit as x approaches, what was it, 4? Yeah, f of x is equal to -2. What is the limit. Okay, now, like I said, you might have gotten the right answer for the wrong reason. So let's be a little bit careful and let's, make sure that we do this correctly. So what we want to be able to do is to use the limit laws, right? So we're going to use the limit laws, and we can do that because we know that both of these limits exist separately, right? So we know that, like, we can just guess this one, right? The limit as x approaches 4 of x squared. That's just, we can just plug that in. That's going to be 4 squared. That's equal to 16. And that the limit as x approaches 4. Okay, so this part, you don't have to do this. Okay, but I really just want to spell it out. So I'm going to split this into two limits like this. Okay, and the reason I can do this is precisely the limit laws. Okay, because I know this limit exists. And because this limit exists, I can say the limit of f of x times f of x is the limit of f of x times the limit of f of x, right? That's what the limit laws allow me to do. And that gives me -2 times -2. Well, let me put brackets in here. -2 times -2, and that's equal to 4. And then again, like I said, you don't have to do it quite in this level of detail. I just want to make sure that we're all on the same page here. Now, when I do this, okay, because I know that each of these two things separately exist, right? Both of these exist. Then I can split that up like so. Okay, we know what those are. We've already computed them. So we got, what do we get? We got 4 plus 16, and that was equal to 20. Okay, so like I said, you don't quite have to do that level of detail. If you wanted to do something like this in a test, I would say, you would say by the limit laws, we know that all the limits here exist, therefore, and you can just write it all out, right? If one of the options was D and E, how do we know if it was? Right, okay, so this is actually tricky because actually, even if you have, well, here, let's maybe switch it up a bit. Okay, here's a question that I have for you. So here's maybe like a bonus question. Okay, and I think this one's probably from, the textbook questions. So suppose we know, and Curdy, I think this is related to what you're asking, but tell me if I got it wrong. Suppose we know that this limit exists. Let's do something like 2, f of x, g of x exists. Must the limit as x approaches 2, f of x exist? Okay, and then I'll do something that I think is slightly more related to, Curdy, what you're asking. But let's start with this one. Does anyone have an opinion on this? Like, if you know that the limit of f times g exists, must both of the limits exist, is basically what I'm saying. Do you know for sure that f exists? Oh, let me make x equals 0, just so that I can do this a little bit easier. Okay, well, how do we solve for it though? Like, what does that mean? But you don't know, okay? Like, if you've watched ahead to continuity, we don't know that these functions are continuous at all. So there's no guarantee that we can like plug in 0 into this function, right? So we have to be a little bit careful. Yeah. So yeah, let's take. It actually shouldn't matter. I can fix it. I can fix it if the limit approach 2. So actually, whether x approaches 2 or 0 shouldn't make a difference. Okay, so here's the tricky thing. The answer is no. Okay, so for example, if I let f of x be equal to 1 over x and g of x be equal to x, right? Then the limit of their product, well, that's just, if I multiply these two things, I just get 1, right? However, f of x does not exist as x approaches 0. Okay, so we have to be careful about that. And the precise reason why this can happen is because as I, hopefully you remember I was saying before from, last week's lectures, when we take a limit, in this case, the limit as x approaches 0, we don't care about what happens at 0. We only care about what happens nearby. So even though 1 over x is really badly behaved at 0, really badly behaved, when I multiply it by just x, that behavior kind of cancels each other out. So this function, right, like this function right here, this is not defined at 0, right? This function looks like it's the function 1 everywhere, but it's not. Okay, plug that function into Desmos, mouse over, the x equals 0 point, and it will say undefined to you. Okay, so not defined at 0. But nonetheless, when I multiplied these two functions together, their bad behaviors sort of canceled each other out. There's nothing we can do about the bad point at 0, but the bad points nearby canceled each other out, right? And so you end up getting something that actually is reasonable. Okay, so the point here is that this is the converse of the limit laws, right? So the limit laws say if the limits exist, if you know that the limits exist, then the limit of f of x times g of x is the limit of f times the limit of g. This was me asking you the opposite question, right? I was asking you, if you know that the limit of f and g exist, can you split it up and conclude that f of x exists? And the answer to that is no. So does that make sense? I just want to make sure that nobody was kind of confused here. Like, the limit laws are still true. There's nothing wrong about the limit laws. And I just want to make sure that, one, we understand this question, and two, you're not confused about how this is different than the limit laws, right? It's the opposite direction of the limit laws. So if there's any confusion about that, don't hesitate to let me know. But wouldn't they exist? Okay, right. So wouldn't they? Sure. Yeah. So there's a couple people bothered by this. Let me clarify the difference. So very quickly, let's just really talk about a little bit of logic. When I say the converse, do people know what converse means? Not like the shoe, but do you know what a converse is, right? So yeah, it's more or less the opposite, right? So for example, let's say I say the following thing: all humans are animals, right? We agree with that statement, right? So if you're human, then you're an animal, right? So humans are animals. Everyone agrees with that statement, right? Humans are animals. So that's a true statement. The converse is if you point the arrow in the opposite direction. Are animals human? Generally not, right? Generally, the opposite direction is not true. Some animals are human, but most of them aren't human. So that's what we mean by the converse. The converse is when you point the arrow in the opposite direction, okay? Is that okay? Because then I'm going to explain the limit laws and their converses, and we can see it, all right? All right, so here's what the limit laws say. So the limit law, in this case, and this thing is true, right? So limit law says if the limit as x approaches c, f of x is equal to L exists, right? So when I say that they're equal to things, I'm saying both exist. Then the limit of their product can be computed as follows. Right? Okay, so this is what the limit law says. This is absolutely true. The converse is what I asked you above, which is if we flip the arrow. Okay, so this is kind of like the human thing, right? We're going to assume that the limits exist, and then that implies that this exists. Maybe let me finish this out. Okay, so the thing in bracket is what we assumed was true, and then that implied that the second thing in brackets is true, right? So the converse is if we flip this around. So the converse here, which is false, right, is the statement if the limit as x approaches c, f of x, g of x exists, right? So I'm starting now with that second bracket, right, and turning it around, then then these limits exist, right? So do you see how I've switched it around? Like I've pointed the arrow in the opposite direction. So that's why it's the converse. That's why it's the opposite, right? And sometimes the converse is also true, but generally not. So in this case, the limit law says if the limits exist separately, then you can compute the limit of the product by computing the product of the limits. The converse is false. If you know that the limit of the product exists, you can't say anything about the individual component functions. Does that help clarify the confusion? Good. Okay. Ahmed, do you want to go like further about what maybe is bugging you? Or we could also do, can you also draw the Converse logo beside the word? Like, wait, like I hope not the shoe Converse logo, right? Because if so, I don't think I'm going to be able to do it. I don't know what it is off the top of my head. Right, but this is
just a star.
Is it just a star? It's probably a fancier star though, right?
I didn't think so.
Okay, I'm gonna write it. I'm gonna do it like that, and then you all can like fill it in. And there you go. There's your Converse logo. Okay. Then why did we say f of x doesn't necessarily exist? Right, precisely. Okay, so I got a direct message saying, why did we say that f of x doesn't exist? Because the converse is false. I'm not saying this is not true. Okay, here I'm gonna put a big X through it. This statement is not true. And the way, direct messenger, that I was saying that it was not true is I gave you a counterexample, right? I showed you that this wasn't true by giving an example of something where f of x times g of x existed, but f of x didn't exist, right? So that's why I don't want anyone to think that this statement is true. That's why I've tried to read it, like write it in red and wrote false. Don't believe that this statement is true. It's not. I'm just writing down what the converse is, and it does turn out to be a false statement. Right? Like I can say false statements. I want you to know that they're false when I say them. Okay, so does that clarify things? The problem above was right, exactly, right? So if we kind of zoom out here, look at what I asked you as the bonus question. I said, suppose that we know that the limit of f and g exists. Does that tell us that the limit of f exists? That really does fall into the converse situation there, right? The same goes if the statement was of the sums instead of the products. Exactly. Yeah. And this is a great question I got as a direct message. Like, is this true if we use sums instead of products? The answer is absolutely. And what I would love for you to do is try and come up with the counterexample yourself, right? So this isn't going to work if we use sums instead. What examples of functions can you give me such that the limit of f plus g exists, but neither f nor g exists, sort of thing, right? Now, as the other sort of caveat that I want to mention, the example that I used, sure. So in this case, basically look at these two functions. They're reciprocals of one another, right? One is just 1 over x. No, it's okay. I'm happy to answer this. One is 1 over x and one is just x, right? So they're reciprocals. And I know when I multiply them together, they're going to cancel each other out, right? They're just going to give me the number 1. So I go ahead and I do that, right? That's what I do in this part right here. And I multiply them together. So this is f times g, right? The limit exists. Nonetheless, if we look at just the limit of f of x, it no longer, it doesn't exist on its own, right? Yeah, okay, perfect. And it's precisely because, the bad behavior of 1 over x and x kind of like cancel each other out. And so they do some nice things. Precisely because, again, the limit is not interested in what happens at 0, just near 0. And that's an important point. Now, the other thing that I don't want to do, or that I want to make sure you all don't do, is accidentally believe the following. So what I will see is something like this. What do I want to do here? Usually the example I would use is trigonometry, but we don't usually do trigonometry. But let me use the trigonometric example. I promise you I'll never give you trigonometry in this course, but I want to use it just because it's an example that we do typically use, okay? So here's an example we might typically give to a 135 student. And we'll say something like, find the limit as x approaches 0 of x sine 1 over x, okay? And this is what they'll do. So their solution, and this is wrong, never ever do this. They'll say, oh, okay, well, I'm going to split that guy up, right? I'm going to write this as like this, x approaches 0 of x times the limit as x approaches 0 of sine 1 over x. Okay, this thing here, this is equal to 0. So that's going to be 0 times whatever this limit is. And we know that 0 times anything is 0, right? Okay, so this is wrong, right? This is very, very wrong. And the thing that they did incorrectly is, remember, look at the yellow above. Okay, what does the limit law say? Look at so we're looking under the yellow thing now at the top. It says both limits. Well, it's okay. No, hold on now. So they didn't do the converse. Okay, it's not that they did the converse, right? So, exactly. Yeah, it is undefined. So in the limit law, it says both of the limits have to exist, right? The limit of f of x must exist and the limit of g of x exist. It turns out this limit does not exist. Okay, and so you can't split it up like that, right? The limit laws explicitly state that for you to be able to do this splitting, you have to know that both of the limits exist to begin with. Okay, you can't split them up if you don't know one of the limits doesn't exist, or if one of them does, or even if you don't know, if one of the limits doesn't exist, you can't split it up like that. So is that okay? Do people understand what I'm saying there? Because it's the same sort of thing. Actually, here, maybe let me do another one. What if I said find the limit as x goes to 0 of x times 1 over x, right? Okay, so we know that number should be 1, right? We already did this example, right? We did this example above. The x's will cancel each other out, and we get 1. We're not allowed to use the limit laws here, because if I did, what would we get? We would get the limit as x approaches 0 of x times the limit as x approaches 0 of 1 over x. Again, I'm not allowed to do this because this thing does not exist. But if we pretended that we were allowed to do this, well, this thing here is equal to 0. So that would give me 0 times the limit as x goes to 0 of 1 over x. And we would say, oh, that's 0, but we know it's 1, right? So did I just prove that 1 is equal to 0? Like, did I explode mathematics and like everything's going to fall apart? No, obviously not, right? Like 1 is not equal to 0. This step right here, this one right here, this was illegal, right? Because again, the limit laws say you have to know both limits exist, okay? And if one of the limits does not exist, you can't split them up like this. So does the limit for the trig example exist if it isn't set? It does actually, and the answer is 0. So it turns out that if you do it this kind of, in this example, if you do it this kind of sort of cockamamie way, like you get the right answer, you get an answer of 0, but you've done it completely wrong. And one of the things that we often have to deal with when we teach 135 is the student will come back and say, well, I got the right answer. And we'll say, yeah, that was lucky. You did it completely and totally wrong. The right answer isn't worth anything because, when in doubt, choose 0, right? Because it's such a special number. But we could have made it be equal to some number. They just got lucky. So does that make sense? Does everyone okay, about how important it is to know that both things exist? This is explicitly a learning objective for us. I'm not saying this just because, I feel that mathematically it's important. It's important that you know that you can only do these limit laws if both limits exist. And we will probably test you on that explicitly, right? So this is something that's important to know. Make sure that you understand it and make sure that if something doesn't make sense, you're asking me right now. Yes, and yeah, exactly. If you go back and look at the limit laws, and in fact, I'm pretty sure if you watch the video where I did this in the limit laws, I'm pretty sure I harped on this point as well. But if you go and you look at the limit laws, it always says, suppose that the limits exist to begin with, and then it makes some sort of statement about them, right? So in summary, limit laws only work when the limits exist. Yes, exactly. That's a great way of putting a summary. You have to know that all of your limits exist to begin with in order to apply your limit laws. And that is universal. That is true for all of the limit laws. Okay? So that is the lesson that I really want you to take from this question. Okay, and if you don't take that lesson, then you can get burned because you might do something incorrectly, okay? Will we be given if the limits exist or not? Generally not, but I mean, in some cases, they exist. So for example, I didn't tell you that 1 over x doesn't exist as x approaches to 0. I kind of expect you to know that. Of course, you also have a calculator accessible to you. You can probably sort it out from that if you really want to. So to answer questions, must we always prove that the limits exist? Basically, if I were doing, the problem that started us out here, like I said, if I was solving this problem even in a solutions for you, I would say, we know that f of x exists. We know that the limit of x exists. Therefore, by applying the limit laws, and then I would just write out, I'd go pretty much straight to here. Right? So you just want to signal that that you're using the limit laws and you know when you're allowed to use them. That's a great little bit of signaling you can do. The limits exist, so by the limit laws, blah. That's a great thing. TA sees that, they're going to be really, really happy. Okay. So if one of the limits doesn't exist, we just plug C into the expression. It depends, right? Like you really have to be, it's really going to depend on what the function is. But as a general rule, you can just try to plug the limiting point into your function and see if you get a reasonable answer out. How do we know when limits exist though? Or how do we find that out? I get confused here. Right, so for the most part, once we talk about continuity, I think things will get a little bit easier because most of the functions that we work with will be continuous and will tell you when you're allowed to plug numbers in. As a general rule, if you can plug the number in and you get something reasonable out, that's usually the limit. Do we need to explain that the limit as x goes to 0 1 over x does not exist, or just say it doesn't exist? I think you're okay to just say it doesn't exist. I think that's okay. Oh, okay. So I got a great question, which why doesn't it make a difference if we approach 0 or 2 in this example? So if I didn't change the function and all I did was change whether x went to 2, then I actually could split this up, right? Because 1 over x now does exist as x approaches 2. But when I was talking earlier, right, because it was before I wrote down this example, if I was doing the limit as x approached 2 and I wanted to create a counterexample, I would have done this one. Right, and so basically I kind of cheated, right? I took the exact same example above and just moved the bad point to 2. So that's why I'm saying, like, whether the question is true or not doesn't matter whether we approach 0 or 2, because no matter what point we chose, I could have just translated it so it was 1 over x minus your bad point. And in effect, I just translated the graph to whichever point we were limiting to. Okay. Okay, so let's do another one. I really like this one. I think there's kind of a good lesson to be learned from this one. And again, you might just get this one by accident, but that's okay, because I think there's a good lesson here. Connie, maybe yes, maybe no. Okay, 30 seconds. Yeah, Curdy, that seems reasonable. That might just be a typo. All right. All right, this is looking good as well. Class is doing pretty good. C again. Yeah, and that is the correct answer as well. So it is F of L. And again, sort of, if you take the, you might have got this because you knew what was going on. You might have gotten it by accident. That's okay as well, though. It doesn't matter. We'll talk about it either way. Let's see what's going on here. So again, what are we told? So we know, so this is question, no, what is this? This is question 4, I'm pretty sure. Yes, this is question 4. Right? And it says, okay, you know that the limit as x approaches, what did I choose? C? Oh no, it was 0. So the limit as x approaches 0, g of x is equal to L, f is continuous. All right, what is the limit as x approaches 0, f of g of x? Okay, now here's the cool thing. So the thing about continuity, and continuity, if you go back and you look at the definition we give you, continuity is basically the statement that you can just plug 0 into your function in order to evaluate the limit. However, you don't know that f composed g is continuous, right? So you know that the limit of g of x approaches L, great, f is continuous. You don't know f composed g is continuous. In situations like this, though, what you can do is put the limit inside the f. That's the same thing as continuity, right? Maybe let's spell this out a little bit more. So recall that f is continuous at C if the limit as x approaches C, f of x is equal to f of C, right? That's the whole point of continuity. You can evaluate the limit just by plugging C into it. Okay, so another way of writing that, the limit as x approaches C, f of x. And what I'm going to do is I'm actually going to take the limit inside the function, like so. Okay, and we know what the limit of x is as x approaches C, right? Like that's not crazy. It's just C, right? And that's the same thing. So what continuity effectively allows us to do is push the limit inside, okay, inside of the continuous function. And that's really convenient when we have questions like this, because even though we might not know that, anything about f composed g, we know f is continuous. So for our problem, right, we're going to take the limit as x approaches 0 of f of g of x. F is continuous, so I'm going to take the limit inside of the f. That is what continuity allows you to do. Okay, it allows you to take the limit inside. Like that. And then we know what this is, right? This is this number right here. So we can now just evaluate, and that gives us f of L, right? And that was C. That's exactly what the answer C was. Okay. Where this can really become useful, and again, where you kind of have to be careful about it, is this is one of these examples where if you just plug in numbers, you can run into trouble. So maybe let me give you a sort of example of that. Okay, so let's say I do something like define g of x to be the following. So let's say I do, let's say I do like the absolute value of x if x does not equal 0, and 10 if x is equal to 0. And then let's say, and let f of x be equal to e to the x, something like that. Okay. And I said, find the limit as x approaches 0 of f of g of x. Okay, this one's a little bit tricky to plug into a computer. It's not impossible, but it's a little bit tricky to do. Okay, and can anyone tell me what is the answer? Like if this was the problem you were doing, what is the answer you would give me? Maybe it's a test question or something. Right, be careful. All of you want to be careful. Actually, so you don't need to take two-sided limits or like two one-sided limits, Curdy, if you do it this way. So Sylvia and a couple of direct messengers said the answer is f of 10, right? So the answer is right, Ariana, exactly. The answer is 1. The answer is not, right, the answer is 1. It's not e to the 10. So we have to be a little bit careful about that. So this is a common place to get tripped up. It is a very easy example. But first things first, somebody tell me, what is the limit? What is the limit as, excuse me, x approaches 0 of g of x? So just forget about f. No, just forget about f. What is the limit of g of x? So it's not 10. Think about what the function is. Right, Ariana, right? Ariana is it's 0. Right, so we want it to be a number, right? Not a function, but you're right. We would look at the absolute value function and we would say, because we don't care about what the function is doing at 0. So you're right. We look at the absolute value function and we say, what is the absolute value function doing as x approaches 0? And the answer to that is 0, right? So if we were to actually like graph this function, it would look something like this. Right, big hole there. And then, you know, the hole filled in at 10. Okay, so the limit here is 0, right? We don't care about what happens at 0, but the limit itself is 0. So we get the limit as x approaches 0 of g of x is equal to 0. So according to our previous, the work that we just did, the exact question that we just finished, so the limit as x approaches 0 of f of g of x is f of the limit as x approaches 0 of g of x. We just said that was 0. So the answer is 1. Why not 10? Right, so again, remember, exactly, we're not looking at what x is doing at 0, only what it's doing near 0, right? So again, kind of like pretend that you're walking along the graph. What I'm asking you is, where are you going? Right? Like there's, exactly, yeah. So, you know, pretend there's a portal at 0. I'm saying, okay, if you walk along the, you know, this path going to this point, I don't want you to step into the portal. The portal is going to like teleport you to the number 10. What the limit is asking you to do is just tell me, where are you going, right? Like what point are you approaching? Don't actually go into the portal, which is going to teleport you. Just tell me where you're like what you seem to be approaching. Like where does the portal, where is it located, right? So that's why the limit is 0. What happens if we get complicated functions? You're going to have to expand on that. As a general rule, you definitely could get complicated functions. But as with anything, when you get complicated functions, you want to try and break it down into easier and easier parts, right? I think like this, even as a question in it. So instead of the absolute value of x, sure. I mean, like, you know, I totally could give you something like the exact same question, but g of x is, you know, x squared plus x minus 6 divided by x squared minus 4, right? And said, now find, you know, again, maybe f of x is equal to e to the x, and then said find the limit as x goes to 0, not 0, of 2 of f of g of x, right? Exact same story. You can't plug in 2 here, right? Because with g of x, you get 0 over 0. So that's a, you know, that limit doesn't make sense. So we can't just plug the number 2 in. The composition f composed g is not continuous at 2. But I can still do something, right? F is continuous, right? That function is continuous. So I can still take that inside, All right. What is that? What is that limit? Does anyone just see it? Can anyone do that one really quickly? Yeah. And as x approaches 2, Connie, what does that become? 5/4. Right. So does that make sense? Does everyone see how, so that's the purpose of this question, right? Is to tell you if the outside function is continuous, but the inside function isn't continuous, that doesn't mean that the world is over, right? What that means is take advantage of the continuity and use that to push the limit as far in as you can so that, you know, you're not actually trying to, like, imagine you computed f of g of x. That thing looks like this, right? And if I said compute the limit of that thing, you might be like, what? How am I supposed to do that? And you might panic. Instead, you kind of break it into 2 parts and try and do, you know, that into pieces. Okay, perfect. Yeah, Josefa, I'm very happy to hear that. For this question, can we just say add f for both sides and which is the answer? I'm not quite sure what you mean by that, Connie. Can you elaborate? Like, oh, like, oh, I see. Oh, you did. You're saying you found, I think this is what you're saying. So you did this is equal to 5/4, and then you basically just put f on both sides. Okay, yes, that does work, but only because f is continuous. Okay, if f is not continuous, you cannot do that. So I don't want you to think that you could just do that with any function. That is not true. It only works because f is continuous here. Okay, so if it's a continuous function, yes. Could you explain what it means to put the limit into f of g of x? Okay, sure. So let me see. Do you know what exactly about that is maybe bugging you? So continuity is what lets me do this, right? So this thing here, let's just type check first of all. That's just a real number, right? And f of something, that's still just a real number. And it's continuity that allows me to do this. So since f is continuous at 2. Okay, so it's continuity that allows me to take the limit inside. And that's literally all you have to do, especially if you're trying to explain this on the test. You say, because f is continuous, I can take this thing. Oops, I deleted way too much. I can take this limit and I can go whoop and put it inside the function instead, right? So it just kind of like phases through the function and shows up inside instead of outside. So the function as x approaches 2 would not be 5/4 and something different. Which function? And same, does that make sense? Do you understand what I'm saying by, like, did I explain that well? Like, let me know if it doesn't. I'm happy to go over it again. What if the inside function was continuous, but the outside function? Oh, yeah. Okay. Yeah. Awesome. Okay, so hold on. So I got a direct question, which is, what if the inside function is continuous and the outside one is not? That is a good question. Then you're in trouble. Like, the answer, it's not too bad, but you basically have to do a little bit more. You can't use any tricks like this. You're going to have to go back to first principles and try and do some sort of factorization. So that's a great question. And I know that that's probably not a super satisfying answer, but yeah, the answer is you're kind of, you know, out of luck. And you got to just attack the whole function sort of holistically, right? Like, I know we can just put the, Emma, potentially, yeah, that's exactly. Like, I know we can just put the limit, but don't understand what it represents. Sure. So yeah, let me see if I can give some sort of nicer intuition for this. Okay, yeah, what the limit says. Okay, so again, remember when we were saying, when you take the limit, if this part confuses you, I want you all to ignore it. Okay, this is important. If this part bugs you, ignore it. So when I say to take a limit right? So let's say I draw a function and it looks something like this, right? And maybe this right here, this is C, and then this is the graph of y equals f of x, right? So when we take the limit, we would say the limit here as x approaches C, f of x, let's say that this height right here, let's say that this is L. Okay, we would say that this limit is equal to L, right? Everyone agrees? Davin, I see it. Don't worry, I'm going to come to you. Everyone agrees this is the limit. The limit is L, right? It's not whatever the dot is. It's, you know, we're ignoring what happens actually at the point and just want to know the behavior of the function nearby. Okay, a function is continuous if you actually do care about what the function is doing at the point, right? So this function is not continuous. But if you know that a function is continuous, what it allows you to do is say, actually, I can care about the point, and the point is the only thing I need to care about. So from an intuitive viewpoint, if I'm, and hopefully I'm doing this okay, it's saying not only do I care about what actually happens as I'm approaching, but I actually care about what happens at that point. And caring about what happens at that point is the process of taking the limit inside the function. Right? The limit has to normally stay outside of the function because you only care about what happens outside of that point. But when I care about that point itself, right, f of C, right? When I put that limit inside, I'm saying actually look at C, actually look at what happens at the limiting point. Does that kind of make sense? Does that help the intuition? Yeah, so the moment I say a function is continuous, I'm saying we actually care about now what happens at the point. So now, you know, before we were only worried about the function away from that point, so the function had to stay outside, the limit had to stay outside, but once it's continuous, I can care about what happens at the point, and that means I can take the limit inside instead. Exactly, exactly. Continuity says you're not worried about the point anymore, so you can put the limit inside and just evaluate away. And be as happy as you could be doing sort of what you want to do, right? Exactly. And if it's discontinuous, you can't do that. Yeah. So hopefully that kind of drives your intuition behind what's happening there. And that is literally what is happening. There's a rigorous definition mathematically of the limit, and that is exactly what happens with continuity, is that you say, I now care about the point, and that's why you can take the limit inside. Okay. Davin, sorry, let me, I wanted to get that out. Let me get to your thing now. Yeah, Wenshi, give me 2 seconds. I just want to answer a direct message that came before you, but I'll do yours for sure. Could you please read, since F is continuous.
Tyler, while you do that, I'm gonna hop out and start the tutorial on the other end.
Yeah. See ya, Aziz.
See ya.
Yeah. So Wenshi, I will do that. Davin, yeah. So the whole point, since yeah, if so, this thing is if F is continuous, then the limit as x approaches C, f of x, or let's say maybe, let me just write this with a generic G, like we don't know anything about G, okay? Then that is equal to f of the limit as x approaches C, g of x, okay? So that allows me to take this limit here and move it inside the function. Okay, Davin, is that good? Does that satisfy what you want? And then Wenshi, I can answer your question once Davin gives me the thumbs up. Yeah, so we can push the limit inside the F. No, it's not a limit law. I mean, you could consider it a limit law if you want. That's just a consequence of continuity. Okay, continuity is what gives you that. So you could call it a limit law, but that's not strictly speaking. Okay, cool. Wenshi, let me do your thing. Let me go back up and find x squared plus x minus 6, x squared minus 4. So we had the limit as x approaches 2 plus x minus 6 over x squared minus 4. Now we have, if we were to plug 2 into this, we would get 0 divided by 0, right? Because we'd get 4 plus 2 minus 6. That's 0 divided by, yeah, exactly. So that says we got to do more. And so what we're probably going to do is try and factor. Anytime you get polynomials and this sort of thing happens, you want to try and do some factoring, right? So if we factor the numerator, we get this. And if we factor the denominator, we get this. And it's these x minus 2 things, right? These are the thing that's bugging us. They're the reasons why it's becoming 0. So because there's an x minus 2 in both terms, we're going to cancel them out. That gives us x plus 3 divided by x plus 2. Now I can plug 2 into this, right? And if I do that, I get 5 over 4 like that. So that's where the 5/4 came from. Perfect. Okay, anyone who has to run, obviously take off if you've got to. And then otherwise, yeah, if you've got questions, ask away because we're technically in office hours now. Can you explain what you mean by continuous? Hala, can you be more specific? Because there's a couple different ways of thinking about continuity. There is the definition. Right, and the definition is exactly this. Right? So that is what it means to be continuous. See, Jack? So continuity means if you want to evaluate the limit, you can just plug C in. So it's a really powerful thing, right? Like you don't have to do any complicated factoring or anything. So if you want to evaluate the limit, you just stick C in and you get the answer. What I'm trying to show you here, though, by virtue of this sort of exercise, is that you can think about it like that, or you can move the limit inside the function. And that is a very useful way of thinking about it as well. So if a function is continuous at a point, the limit always exists. Right? So that is a requirement because f of c has to exist, right? Like we're saying if f of c doesn't exist there, then this limit doesn't exist. So when a function is continuous, it definitely always exists. So how is that okay? Does that work out? Usually we're not as concerned about whether it exists or not. We use continuity to help us figure out what the value of a function, what the limit actually is. And when your function is continuous, it's very easy to compute the limit because you just plug the number into the function. But most of the time we know we can't do that, right? Or not most of the time, but there's lots of the time where we can't do that. Okay, so I have a direct message question, which is asking me to talk about 3C. Now, I don't want to talk about 3C directly, obviously, because it is a question, but we did have a similar one to this that we did last week, which I'm happy to bring back up, and I'm willing to bet there's a bunch of people who are interested in that as well. So maybe let me just pull up last week's questions. All right. Yeah, exactly. Yeah, I was asked about the writing assignment. So here's a problem, and maybe let me just kind of copy it over, and hopefully that does not grab the Zoom meeting when I did that. We're going to find out in a second here. It did grab the Zoom meeting, so let me do this again. We'll move the Zoom meeting down here. Why? Oh, because I'm already at the bottom. That's why. No, what are you doing? There we go. Okay. So Hala, if you look in, if you go to the meetings page, find my lecture 9104, there will be a link. And if you click it, it'll pull up the recordings from last week. Let me know if you can't find it. I can share a screen and show you where it is. But yeah, try and find it. And if you can't, let me know. Yeah, so same sort of story here, right? We've got this function on the interval -5 to 5. And we want to evaluate the function of f of x as x approaches 1, right? So it's a very, very similar question. Again, we kind of have to like break it into two pieces, right? We want to look at what happens as x approaches 1 from the right. So I would say something like as x approaches 1 from the right, f of x not only approaches 1, fx is actually equal to 1. Right? But moreover, f of x is actually equal to 1, right? So then if I take this and plug this into f of x, right? We said this thing is actually equal to 1. So I'm going to get f of 1, and f of 1 here is equal to 3, right? Because 3 is this number right here, right? That's f of 1. Okay. As I approach from the left, though, I actually get something else. So as x approaches 1 from the left, f of x is still approaching 1, but this time it's approaching 1 from below, right? So if we go to the graph and I walk this path as I'm approaching 1, I am approaching 1, but I'm approaching it from below, right? And so when I plug that into f of x, right, we said this thing is approaching 1 from the left. So the whole limit becomes the approaching 1 from the left. And that gives me what? 1. And then since these two things are not equal, that means the limit does not exist. So the limit x approaches 1, f of x does not exist, right? And that's why we choose D for that, right? Okay, Sylvia, give me a second. How did I decide that f of x equals 1? Okay, yeah, sure. So here, let me zoom in here. Okay, so I'm approaching, right, as x approaches 1 from the right, I'm walking on this path here, right? And on that path, I'm not just approaching 1, I'm actually equal to 1, right? Right, I'm not like swooping in from above, I'm not swooping in from below, I'm on 1 the entire time. I'm exactly equal to 1. Does that make sense? Okay, yeah, because I broke it into 2 pieces, right? So I'm looking at as x approaches 1 from the right. So here's the point 1, right? This is x equals 1. And I'm approaching that line from the right. Well, there's only, the function, there's only one part of the function that approaches that line from the right-hand side, right? So if this function had looked like something else, if this function had looked like this, right, and I was approaching along this line, I would have said, oh, f of x here seems to be approaching 1 from above. Well, what about the other blue lines? Because we don't care about the other blue lines, right? Because we're approaching the number 1, right? Like this black line here is the number 1, so we're going to approach it. And this is the only blue line that approaches this. Yeah. Okay, does that make sense? And then I got a direct message asking me to maybe go over the approaching. Yeah, no problem. And then, so I got another direct message saying, okay, well, can we do x approaching -1, or sorry, x approaching 1 from the left again? So again, suppose that, I'm walking on this line now. Right, so I'm approaching 1, but this time from the left-hand side. Okay, so what's the y value that I'm approaching? Well, the y value that I'm approaching, oh, that yellow doesn't show up very well, I don't think. So I'm approaching this y value, that's 1, right? But in particular, I'm approaching it before, or sorry, from below, right? So as x approaches 1 from the left, f of x is also approaching 1, but it is also approaching 1 from below, right? Oh, how do I get, yeah, sure. Okay, so what I did is once I knew that, f of x was actually just equal to 1, that told me that the limit as x approached 1 from the right, f of x, there's no more limits. I can just plug in f of 1, right? And so if I look at f of 1, what I'm going to do is I'm going to look, there's a hole here, right? There's a hole. So where is f of 1? It's not there because there's a hole. F of 1 is right here. Right? And what's the y value there? Oh, it's 3. Because we want f of 1, right? So I just want to know what is the value of the function at 1. And that just happens to be that point, right? Like if this point were somewhere else, so if I delete this, and yeah, let's say here, let me see if I can just wipe that out. So let's say I moved that point to here instead, then the value would have been 2, right? Because I'm taking the limit, right, yeah. Yeah, exactly, it's given in the picture, yeah. No problem. Isn't f(x) just approaching 1 from the right instead of being 1? No, it's actually exactly equal to. So you're talking about when we approach from the right? So not the, yeah, okay. So it's not approaching from the right though, right? Because you want to think about the y value, right? So what is the y value at this point right here? Right, what's the y value at this point? And the y value at this point, right? Yeah, it's all just ones. So I'm not bigger than 1 and getting closer to 1. I'm not lower, like less than 1 and approaching 1. I'm just exactly equal to 1, right? Versus when I approach from the left, like along this path, right here, I'm 0, and then I'm like, a half, and then 3/4, and then 7/8. And so I'm approaching 1 in that case, but I'm always less than 1. So yeah, in this case, when you're doing that double composition, you want to look at where is the function approaching from. Exactly. I'm not approaching 1, I am 1, right? Exactly. I'm not approaching from above. I'm not approaching from below. I am exactly 1. So that's very special to these straight lines, right? Like most of the time that's not going to happen, but in this case it does, just because it happens to be constant as I approach from the right. Could you? Yeah, sure. All right, Sylvia, give me a second here. I just need to download your thing. And then Kelly, I see yours. Give me a second. Sylvia was up here first, but I've like lost it in the chat because it was long enough ago. Let's see. Oh, yes. Okay, this question, sure. Sure, Curtia, I can do that. Here, let me just write this down. So Kelly, you're asking 5.8 H and G, and then Curdy limit X approaches 0. The circled one, sure. Yeah, okay, so remember we said f of x is approaching 1 from the right or from the left. So basically when I do f of x, okay, the first f of x is doing this, right? Turns out when I do f of x, I'm doing that again. And so, right, like I basically end up, the first f of x, I do this. Oh, I'm approaching 1 from the left. Oh, but that's exactly what this limit was doing as well. And so that's why I get 1 as the final answer there. Yeah. Okay, so Sylvia, your question was from week 1. I don't remember which one it is, but it's this one. There's actually a good Piazza question on this. I think it's public. So Does anyone have that link? Let me see if I can find it. But yeah, no, there's a good Piazza question on this. So I want to see if I can, oh, no, that's the wrong class. Where is it? Nope, that's not it. Here it is. Okay, I'm going to throw this in the chat, everyone. So I can talk about this, but like we do go over this one, and this is great because there's like some student answers to this, and I've helped a lot for this as well. But basically what you do is, again, so we're going to set y is equal to e to the x minus e to the negative x divided by 2. If I multiply both sides by 2, that gives me 2y equals e to the x minus e to the negative x. Then I'm going to multiply everything by e to the x. And I'm deliberately going to write it like this instead of simplifying it. And then if I put everything on one side, I'm going to get e to the x squared minus 2y e to the x minus 1 equals 0. Okay. And then the point is that this is a quadratic equation. In e to the x. So you can solve it using the quadratic formula. And then continue to solve for x in that way. Does that make sense, Sylvia? Like I didn't do the whole thing, but from there you can see if you can finish it off. And again, the whole answer I think is given in that Piazza question. And Hala, yeah, that's fine. Throw it up and then I'll add it to the list. Yeah, for sure. So Sylvia, give it a try. And if it's still bugging you, don't hesitate. And if there's time in office hours, ask me again about it. Or again, you can throw it on Piazza. And again, that Piazza link does have a student who finished the calculation. And so you can check it from there, right? Okay, 1.9 B and C, sure. Okay, so Kelly, you asked 5.8 H and G. Wait a second. That doesn't exist for me. Kelly, are you looking at the PDF? The PDF of the book? And exercise 5-8. Yeah, I don't have that here. Let me show you what I've got. And if it's nearby, you can tell me. Maybe my version is a little bit different. It shouldn't be, but maybe it is. Okay, so here's my copy of the book. I don't have a G and H in 5-8. Do you see the question that you're interested in? 5-11, this one? Okay, and G and H here, so these two. These are, did we do horizontal asymptotes? I'm trying to remember. So, because if we didn't do horizontal asymptotes, I wouldn't worry about those, but I'm trying to remember if I actually made you do them. Did I make you do them? Yeah, I don't think we did. So I wouldn't worry about G and H, actually. You can skip these. Do you want to know how? I'll show them how to do them anyway, if you really want, but we're not doing limits as you go to infinity. So you can skip those if you want. And that means you can skip I as well. Actually, you can skip all of 5-11. Did I? Oh, you know what? I did accidentally put it in the exercise problems as something you could do. I would skip all of 5-11. Yeah, always. Yeah, we're not going to do horizontal and vertical asymptotes. There was a time in the course where we did, but we're not doing them this year. So you can skip 5-11 in its totality. Yeah. Uh, 12B. Okay, I'll add it. Yeah. Well, I mean, that's what we were doing instead. So I can do 12b instead. Sure, I'll do that. Okay, so 5-12b. So this is, you've got this thing, f of x is the limit, is f of it's ax plus 2b. When x is less than 0, it's x squared plus 3a minus b. When x is between 0 and 2. This is less than or equal. Doesn't make a difference. And then 3x minus 5 when x is greater than 2, right? And you want to find a and b such that f is continuous. Okay, so these functions are generally continuous everywhere. Because it's a piecewise function, the only place we could really run into trouble is where the pieces join, right? Does that make sense? And I can't graph this for you because we don't know what a and b are, but yeah, the places where these functions join are really the only places that we can have trouble. So what we want to do is we want to look at x equals 0 and x equals 2. Okay, so let's start by doing the limit as x approaches 0 from the left, f of x. No problem, Sam. See you later. Can anyone tell me, as I approach 0 from the left, what is the limit of f of x? Yeah, Kelly, that's the right function. So now let x be 0. Oh, no, let x be 0, not 1. Right, just 2b, right? So because we're less than 0, so this is going to be the limit as x approaches 0 of ax plus 2b, right? But when x is 0, yeah, exactly. The a disappears, and we're just going to get 2b like that, right? Okay, same thing. So we're going to approach now the limit as 0 approaches from the right, f of x. What function do I use for this one? Yeah, okay, 3a minus b. Yeah, exactly, the second row. So x squared plus 3a minus b. And if I plug x squared equals 0 into this, I get 3a minus b, okay? Oh, right, yeah, no, there isn't an, is it 3ax? It just says 3a, so maybe it was a typo, but as it is right now, it just says 3a minus b, right? So if I plug x equals 0 into this, this part dies, but this part still lives. So it's 3a minus b. But we'll see if that gives us something inconsistent later, right? Okay, and these have to be equal, right? Because the limits have to exist. If you're continuous, your limits exist everywhere. So these have to be equal, right? So 3a minus b has to be equal to 2b. Okay, or if we want, we could do something like 3a minus 3b is equal to 0. And that's the same thing as a minus b is equal to 0, or a is equal to b, right? Well, but there are actually infinitely many solutions, right? We can't determine uniquely what a and b are here. So let's go to the second equation now. Let's look at what happens when x is equal to 2, right? So as limit as x approaches 2 from the left is what? Which function do we use? From the left, though. Yeah, second row this time, right? Because we're still in this regime, right? We're less than 2, right? Does that make sense? Oh, so I subtracted 2b from both sides, and that gave me 3a minus 3b. And if it was from above, it'd be the last row, exactly, which we're going to do in a second anyway. Yeah. Okay, and so now the limit as x approaches 2 from the right f of x is the, now we use the last row, right? So 3x minus 5, and that is what, 1? So we get that 4 plus 3a minus b has to be equal to 1, because again, these two things have to be equal. And so we get 3a minus b is equal to 5. Well, that's two equations and two unknowns. So is it, wait, okay, did I screw something up there? Is what, oh, yeah, you're right. I can't add. Thank you, everyone. All right. And now you can figure out what a and b have to be, right? So a has to be equal to b. So let's see, 2a. So a is -3/2. A and b are both -3/2, I think is the solution to this, if you work it out. All right. It's -3. That's not. Anyway, so the point is, here's an interesting, yeah, exactly. I got -3/2. But so the interesting thing you can see here is we could make linear algebra show up, right? Because what if I gave you more piecewise functions and more variables? All of a sudden, yeah, exactly. You have to solve it simultaneously. So all of a sudden, then you have multiple equations and multiple unknowns. And how do you solve that system? Oh, you have to write it as a matrix, plug it into a linear system, row reduce it, right? That's totally fair game, because you all know how to solve linear systems of equations. So that stuff doesn't necessarily vanish and disappear just because we're not talking about it anymore. Yeah. Wouldn't that be a fun test question? Well, I think it would be a fun test question. No, I mean, like, depends on what you mean by fun. My mentor, Alfonso, may he rest in peace, always used to explain, yeah, he always said the following. He said, when you make a test, if it's interesting, it's too hard. If it's easy, it's too hard. If it's trivial, then it's the right difficulty level. So that's how he used to make tests, and he always made tests that were trivial. But if you ever go and you ask students, how were Alfonso's tests, I think as a general rule, they all thought they were hard. So it's because, it's supposed to be trivial for us. How do we make our own? This is a great question. So one of the things that you can do is take a lot of the questions that we've given you today and change around the numbers a bit. I mean, the graphs that I've given you are a little bit hard to make. They're hard for me to make, so I wouldn't expect you to make them. But as a general rule, take questions, try and change the numbers around. You could even take this function, right? And just try adding another piece to it. So maybe, you made something up and maybe it was, 2ba plus x squared or something. And then you change this to 2 is less than x is less than equal to 4, right? And just make something up. Who knows? Maybe it'll work, maybe it won't work. But just change it around a little bit, and boom, all of a sudden now you've got something that you can practice with. And if you get stuck on it, you can ask Piazza. And we're always super happy when students make their own questions and are asking about them. We're really excited to answer those questions, so don't worry about that. If you want to make questions for other people, for example, when we were doing this question, right? So when I make these sorts of questions for you, I start here, right? That's true. That is true. Sometimes the numbers don't work out. So there is a little bit of cleverness that does actually go into making questions. So here's an example. When I make these questions, obviously for making this question for yourself, it's tricky because you already know what the answer is, right? So when I'm making this question for you, I start with the already factored form and then re-expand it, right? This is why when you make a practice test, you usually don't want to make it for yourself. You want to make it for a friend, and then your friend hopefully makes a practice test for you, because in the process of making this test, you usually know how the answer would work out, right? Same thing, even when I made this question, right? The original version of this question, I just did a bunch of trial and error until I found values of A and B, and I would modify the function a little bit to give me the numbers that I wanted. But when you do that, you then know the answer. So the practice test isn't any good for you. So you would make it and you would want to give it to a friend and then have them do the same thing back. And if you want to get ahead, talk ahead of time and say, hey, I'm going to make you one of these questions. Will you make me one of those questions? That's a great way of doing it, right? So it is difficult to make your own practice questions unless you're just willing to throw stuff against the wall and see what sticks. Otherwise, try and find someone else in the class who you're willing to kind of exchange with. That's definitely the best way of doing it. Okay. Curdy, you wanted absolute value of x over x. So the limit as we approach 0. Okay, so let me graph this function. And once you see the graph, you're like, oh, okay, I see what the answer should be, but how do we do that, with like algebra and calculations? So the graph of this function looks like this. That's not a straight line. Let's try that. Okay, so this is what the graph of this function looks like. And those are just straight lines, right? This is -1 and this is +1. All right, so how would we actually do this as a limit, right? How would we set this up? So we're going to want to do two one-sided limits because the two-sided limit just doesn't exist, right? By inspection, we've got this big gap here. So we want to take the limit as x, or actually, you know what? Maybe let's recall something. So let's say recall the absolute value of x is x if x is greater than or equal to 0 and negative x if x is less than 0, right? Do we remember that? Everyone's okay? That this is the definition? Okay, good. Because this is super important here, right? Like we need to remember this definition because this is how we're going to do it. So when I take the limit as x approaches 0 from the right, when I do this, I'm assuming x is greater than 0. Right? If I approach 0 from the right, I'm bigger than 0. So if I'm bigger than 0, then the absolute value of x is just equal to x. Like that. Does that make sense? And it's the exact same thing that we did in the piecewise function above here, right? Wherever it is. Oh man, I have to go so far up. When we did this piecewise function, just like the absolute value, right? The absolute value is just a fancy piecewise function. Yes, yeah, that rule is always true for the absolute value. Absolutely. And the absolute value, again, is just shorthand for this fancy piecewise function, right? So when we did the limit of 512b, above, right, and we were doing these one-sided limits, we would just figure out which of these functions applied. We're going to do the exact same thing for the absolute value, right? Like I know that some students are kind of thrown off by the absolute value, but we're going to do the left-hand side too. I want to make sure that we're comfortable with the right-hand side. Yeah, right. So you do it, just treat it like any other piecewise function. Okay, it's nothing special. I remember too, I really hated it when absolute values would show up, but if you remember, it's just a piecewise function and you just treat it the exact same way, then it's not too bad, right? So here, x is less than 0. Okay, that means that we are now in this regime. So the absolute value of x is equal to negative x. All right, and that gives me -1. And these are not equal. So even though the one-sided limits do exist, but the two-sided limit does not because these two things are not equal. All right. So does that make sense? No problem. Sweet. Good to hear. And then 1.9 B and C go all the way back. Yeah, exactly. It does make sure that the number just comes out positive. And that is a good way of thinking about it. But the problem is that when you want to manipulate it, that definition of thinking about the absolute value as just turning something positive becomes tricky, because if you don't know what X is, like you don't know whether to just drop the absolute values or to like switch the signs, right? So the benefit of using this definition of the absolute value is it gives you something you can sink your teeth into, right, algebraically, and that way you can actually start to do manipulations. So every single time you get an absolute value, you want to use this piecewise definition of it in order to be able to do stuff. That's definitely the right thing to do. And once you learn that lesson, that you should just always use that, absolute values are not too scary anymore. Okay. So B and C here. So what do we got? So we've got, instead of asking if the limit is x approaching 1, I ask myself, what would happen if x approached -2 instead of the function? Yeah, Kelly, give me a second. Let me do this one quickly because it was on the list before you. Okay, so this is 1.9b. So we've got f of x. Ooh, yeah, this is kind of dirty, right? F of x is equal to x e to the x, and g of x is just equal to e to the x. And what do we want to find? F compose g, right? So find f compose g. Okay, so f of g of x means that everywhere we see an x in here, we're going to put g of x, right? Okay, sure. Yeah, I mean, in this case, oh, so maybe that one's better for C, right? Because in this one, there's not too many. Well, here, let's just write it out. So there's g of x, e to the g of x, right? And then if I take that and plug that in, I get e to the x, e to the e to the x. And if you really want to, you can write that like that. All right, so that makes sense for B. Is it maybe this last step? Because I know this one sometimes bugs people. But the answer is probably written like that. What does the answer key say? Here, let me see if I can pull it up. Oh yeah, I'm in the wrong thing. Lecture notes, MAT133, solutions. 1.9. Oh yeah, that is a typo. Good catch. Yeah, no, I see it. It says 1 plus e to the x in the exponent, right? Yeah, that is a typo. It should be x plus e to the x. Yeah, so you caught a typo there. Okay, good job, Hala. Let me actually do it. Yeah, it definitely does happen. Over the years, there are less and less because students will point it out. I'm literally gonna fix it right now, because if I don't, I will forget. Is it -5 to 1.9? There. Okay. Yeah, 1.9a, I think is. What are you saying? You think there's another one there? Okay, here, let's just do it quick. So 1.9a. So we've got what? F of x is 2x minus 3. And it's possible as well that the questions have changed over the years, because that sometimes happens. And we want f compose g. So we're going to get f of g of x. That's going to be 2 times x squared plus 1 minus 3, right? It's going to be 2x squared minus 1. And what does the solution say? Why aren't you working? Solutions say, oh, it says 2x squared minus 2. Man, how is keeping off by 1? Okay. And then you wanted C as well, right? Good catch on these. In all these years, I think you might be the only person to have caught these. So C is, yeah, so you're the only one who's actually doing them correctly or doing them or both, right? And there's nothing wrong with that whatsoever. Okay, g of x is equal to x ln x squared plus 1. Okay, so f of g of x is going to be e to the x ln x squared plus 1. Now, what we want to do is we want to get rid of the e and the ln, right? Like we want to cancel them out. But in order to do that, I have to have just e to the ln. So what I'm going to do is I'm going to take this guy and make it the exponent of that. So I'm going to write that like x squared plus 1 to the x. Now the e and the ln cancel out, and I get that. And is that what the solutions say? Do we finally have one that's correct? Oh, I think that one is actually right in the solutions. So is that one, the algebra there is bugging you at all? Because is that one okay, or do you get how that one works? Right, yeah. Or the other thing you can do is remember e to the ab is the same thing as e to the a to the power of b. So instead, what you could have done from here is you could have said this is e ln x squared plus 1 all to the power of x, right? And then the e and the ln cancel, and you would get the same thing, right? So you could do it that way. Could you have brought it down next to the e? Depends on what you mean, but no, it's going to always end up working out as x squared plus 1 to the power of x. So you want to like somehow bring the x down here. No? Okay, what did you want to do? Okay. What about it? Like just x squared plus 1? I mean, there has to be that x there, right? If you just plug this into a calculator with x being equal to like 2 or something, you'll see you don't get 5, you get 25. Right? Like you can't, the x can't disappear anywhere. It's got to hang out. Mm-hmm. Yeah, you got to do something with it. Because yeah, if the answer is just x squared plus 1, you basically just get rid of this x somehow. But you can't just get rid of stuff, right? So if some sort of algebra you did ended up making that disappear, then there was some mistake somewhere in there. Yeah, it should be x squared plus 1 to the x. Okay. Kelly, you had a question. So the last question in week 1 poll, which I actually think is this question, right? Kelly, am I wrong? Yeah, okay. So in this question, I gotta scroll up again and find your thing. Just want to make sure if I'm doing it correctly. Instead of asking the limit as x approaches to 1 f of x, I ask myself what would happen when x approaches -2 instead. Okay, so when you say you're just changing the question, yes, Kelly? You're changing it so that instead of x approaching 1, x is approaching -2. Is that my understanding? Okay. Okay. And now you're trying to redo the problem. Okay, so, and to determine the function, we want to look at the one-sided limit instead of the function. Yes, that's correct. Yeah, you want to look at the one-sided limits here, right? Yeah, so your understanding of that is fine. Do you want me to go into more detail? But yeah, exactly. Okay, yeah. Yeah, and then look at the one-sided limits. As you approach from the left, you're going to get the same sort of thing because it's constant from the left. It's very similar to this question where you approach 1. Yeah. No problem. Okay, anyone else? Anything else? I think that was all the questions that I had on my list. So, I mean, if there's another thing, please don't hesitate to ask. Otherwise, we can just call off Sarah's. We don't have to do the whole thing. It's up to you. See you, Curdy. Which is 570? Like, are you asking what the answer is, Kelly? Okay, cool. See ya, Emma. Yeah, okay, here, let me look at it too. Uh, 112, 113, sure. Let me just get the answer here for Kelly so that she can check for answers correct. So as I approach, so this is actually -1. Right. And then just cross check. You got -2. Of F, right? Yeah, it is DNE. I got DNE. And I just did it again now. Okay. Yeah, so I got DNE, Kelly. I'll come back to that. Keep trying it. But basically, so what does the inside function do as you approach x? As x approaches 1 from the right, what does negative e to the x minus 1 do? And then hala, I'm going to 112 right now. Approach what? So as x approaches 1 from the right, what does negative e to the x minus 1 do? Okay, 112. Ooh, this is a good one. This is yeah, this is nice. So let me just kind of do one here, Hala, to give you an idea of what to do for the other ones, and then you can try the other ones on your own. So Kelly, let me know when you've got something for this and I'll come back to it. So for like 112, let's maybe do C or something, right? So we know F is odd, right? Let's remind ourselves what that means. That means that this is true, right? And we know that G is even. So that means the G of negative X equals G of X, okay? And okay, so everything, anytime you're trying to figure out even and oddness, what do? You plug negative X into your function and you see, does the negative sign come out? Does it disappear? Or does it do something else entirely, right? Because it's possible that a function is neither even nor odd. So that's what we're going to do. So we now want to figure out is what is, let's say, f plus g. Okay, so I'm going to plug negative x into this. And if I do that, I get f of negative x plus g of negative x. Well, f is odd, so I can pull the minus sign out. G is even, so the negative sign does not come out. That's neither f plus g nor negative f plus g. So this is just neither. Does that make sense? Like if it were odd, there'd have to be a minus sign in front of both. If it were even, there'd be no minus sign in front of either. It's just neither of those two things. There is one minus sign and then the other thing doesn't have a minus sign, right? So we can't say anything. For f times g, we can do something similar. Negative x is f of negative x, g of negative x. And again, let's use it. So f is odd, so the minus sign will come out. G is even, so there isn't another minus sign. Yeah, so that is negative f times g. So this is an odd function, right? And then for the third one, f of g of negative x, g is even, so the minus sign just disappears. And yep, that is just f composed g. So we get even. Does that make sense? So you're just going to plug negative x into your function and then use what you know about, I'm not sure how you're making correlation between the signs and whether the number, whether the function is even or odd, right? Okay. Here, let's look at 2 again, because maybe it's easier when we're actually even or odd. So if fg is even, then we should get that fg of negative x is fg of x, right? And if it's odd, if fg of negative x equals negative fg of x, right? So in both of those cases, I'm going to plug in negative x, right? So I do that up here. And I want to see, does the thing I get out, does it have a minus sign in front of fg, right? This is f times g. Is it negative fg? Is it just fg? Or is it something completely and totally different, right? And in this case, we get negative fg of x. And so this function is odd, right? That it's the blue thing. Does that make sense? Do you see, right? I'm trying to see, like, does the minus sign come out or not? And in this case, it does. Yeah, if it comes out, it's odd. If it doesn't come out, it's even. Note in part 1, it is neither though, right? Because it does come out of the f, but it doesn't come out of the g. So if it were even, we would get f plus g of x, sorry, of negative x is f plus g of x. If it were odd, we would get f plus g of negative x is negative f plus g of x, right? This is neither of those two things, right? The first thing is f of x plus g of x, right? This thing here is f of x plus g of x. This thing here is negative f of x minus g of x. And this thing is neither of those two things, right? It is neither f plus g nor negative f minus negative g. It's something in between. So that tells us it's neither. So you just keep playing around with these and see how, you know, how these fan out. Like, can you pull out the minus signs or not? I'll tell you that for like composition and multiplication of the functions, you'll always get either even or odd. For addition, it is really going to depend. And you could get even, you could get odd, you could get neither. Okay, so that is kind of like a nice little litmus test that you can use to see if things make sense. Okay, for 13, without kind of going too much in this, because there's a couple more questions I want to answer. So remember, you're going to set y is equal to ax plus b over cx plus d, and just actually try and solve this thing, right? So multiply both sides by cx plus d. Expand out, collect all the x's on one side, collect all the y's on the other side, and solve for x, right? And you'll end up finding that when you get your answer, try composing, right? So remember, if you get f of x is ax plus b over cx plus d, you'll get f inverse, and actually try computing what f of f inverse of x is. And you'll see that something has to be true. Like one of those letters can't, some of the numbers can't be 0 or something along these lines. I know exactly what the condition is, but I don't want to say it because it's a cool thing when you see it. But once you compute what the inverse is, plug it back into f, and you'll get a condition that comes out. Okay, so that's how you do that one. Okay, perfect, awesome. Christian, don't worry, I haven't forgotten you. I quickly explain 5.7 of. Oh, wait a second. Yeah, so that's interesting because that's what Kelly was asking too, right? It was 5.7, I believe. Let's see. Yeah, so Kelly and I right now, we're working on 5.7D. Right, so we're looking at the limit as x approaches 1 of f of negative e to the x minus 1. Okay, so I was asking, right, this came up. Like, of course, we're going to break this into two one-sided limits because that's pretty much how you do all these questions. So let's approach 1 from the right. So as I approach 1 from the right, what does negative e to the x minus 1 do? Okay, Kelly, did you start this out? It is fx approaching negative 1 when x is approaching 1 from the right. Okay, yes. So this is approaching negative 1, but we can go further than that. Is this approaching negative 1 from above or from below? Like, what should I put here? Should I put a plus or a minus? Not above. Yeah, it's approaching from below. Right? So here's how you can figure it out. So negative e, so let's try, like, if we were to plug in x equals 1.1, right? Because I'm approaching x from above, right? From to the right. So when I plug 1.1 into this, I get negative e to the 0.1. That number is, what is it? It's actually less than negative 1. Yeah, exactly. If you want, you can think about it like that too. So you can think about it in terms of like a graph, and the graph looks something like this. Right? And so here's, x equals 1. Right, exactly. And so now, as x approaches 1, we get negative e to the x minus 1 approaches negative 1 from the right. So we would get limit as x approaches 1 from the right, f of negative e to the x minus 1 is the limit as x approaches negative 1 from the left, f of x. And if we look at the graph, I got 1 out of this. Right? Christian, does that make sense too? Do you see that? Exactly. And Kelly, you did the same thing for the other side, and you're going to get a different answer, and it's not, that's why it does not exist. Okay, cool. So does that explain like how you play with? And so when you do f of x, you do the exact same analysis that we just did for this function, except you do it with the graph that you have instead of, plotting this in Desmos or something. Are there any ways to do it without plugging? I mean, really, we're not plugging anything in. We're just analyzing the behavior of these functions as they're approaching particular numbers. But the way that I've kind of described it to you here is the only way you can do it. Like, I know, basically the way I did this, for example, is I know that e to the x, as x approaches 0, let's say from the right, e to the x approaches 1 from the right. And so when we flipped it, when we put the x minus 1 in here, right? So that means that as x approaches 1 from the right, e to the x minus 1 approaches 1 from the right. And then when we flip the signs, when we throw the minus sign in there, we reflect about the x-axis, and that's going to flip whether we're approaching from above or below. So as x approaches 1 from the right, negative e to the x minus 1 approaches negative 1 from the left. Right, so if you want to do it without graphing or anything like that, that's kind of how you do it. You kind of have to start with what you know, which is something about e to the x, and iteratively construct to what you're going for. Yeah, no problem. Christian, you're good. Do you need me to talk about anything else? Or you're fine with what's there? Or? All right, cool. All right, everyone, we're at 7 o'clock. Hopefully, I think I answered all the questions that were outstanding. So hopefully, yeah, no problem, Ariana. Yeah, everyone, thanks for coming around. Have a good Wednesday. And yeah, we'll see you on Thursday. Okay, ciao.